There's always more than one way to look at a problem, and when it comes to remyelination, perhaps it's important to try and figure out what keeps the MS brain from remyelinating on its own if the normal brain tends to do all that automatically. Well, hello, and welcome to another episode of You and Me and Multiple Sclerosis. My name is Pam, and I've been living with MS for over 40 years. And as you know, every chance I get, I talk about remyelination because I really do think that it is critical for regaining function for those who still have enough axons to make a difference. And that would be, probably lots of people. I don't know about me, honestly. When I look at scans of my brain, I think, well, there's not much there to remyelinate. Be that as it may, I'm still excited about this technology, and I'd like to see it advance to the point where people can actually be trying it out. I found an interesting article, so go ahead and take a look at that. I saw this article from the National Multiple Sclerosis Society, published on August 29th of 2025, and it's called National MS Society Funded Study Points to Potential New Myelin Repair Strategy. They say that researchers from Case Western Reserve University discovered that a protein called SOX6 acts like a molecular brake, keeping brain cells from maturing into myelin-producing cells. Identifying ways to lower SOX6 levels could have important implications for myelin repair. This study was supported through a 2024 request for proposals. National MS Society staff recognized the need to accelerate research on myelin repair and nerve cell protection and funded the most promising projects. And here's some background. In MS, the body's immune system damages myelin, the protective coating around nerve cells, leading to disability over time. And it's important to point out everybody's body damages myelin, or myelin just degrades over time. But with most people, the repair mechanisms are robust enough that there's an equilibrium that happens between the damage and the repair. With people with MS, however, the damage component far outstrips the repair component. They say that myelin repair is possible but is ineffective in MS. Oligodendrocytes make and repair myelin, but these specialized brain cells must first mature. In MS, the cells often remain stuck in an immature state. Understanding what controls the maturation process could be key to developing new treatment strategies that restore myelin and improve function in people with MS. And here's what the study entails. Researchers at Case Western Reserve University used multiple approaches, including lab-grown cells, mouse models, and donated human brain tissue to study molecular changes that occurred as immature oligodendrocytes matured into myelin-producing cells, and to test strategies that could strengthen this process. And here are the results. The group found that one protein called SOX6 keeps immature oligodendrocytes stuck in their early stage and unable to repair damaged myelin. Brain tissue from people with MS showed unusually high numbers of cells with this SOX6 immature signature. Researchers then reduced SOX6 levels in mice. When SOX6 levels were lowered, oligodendrocytes matured quickly and myelin production increased throughout the brain. That's pretty exciting to have a very direct cause and effect that's so obvious. That doesn't often happen, but pretty neat that they found it in this study. And of course, the question we're all asking, why does this even matter? Well, targeting SOX6 could release the brake on myelin repair. Unlike current MS treatments that mainly focus on controlling the immune system, an SOX6-based therapy could instead encourage production of new myelin, offering hope to restore nerve function and slow or even reverse disability in MS. Well, I'm all for that. And then we can look at some video clips of the investigators who have been working on this very interesting angle for solving the remyelination problem.
The first topic that we're going to jump into is on a more broad basis right now. Talk a little bit about what remyelination is in the context of multiple sclerosis and how our understanding of remyelination has evolved through recent advances in research. And I'll give anybody the floor to start.
Maybe I would just say remyelination in the context of MS is the restoration of the normal, hopefully normal or near normal architecture of the insulating substance of myelin in the brain. And it's a critical step towards recovery of function, but also preservation of function over the long term. So, our understanding has evolved substantially. I mean, there's a lot of nuance to getting myelin back the way that it was originally in development. That includes how many wraps of myelin you have, what the spacing is in between myelin segments, tons of different features of how much does that actually encode normal function. We're learning, I think, about that, and how much does activity modulate that normal myelination. So those are all areas we've got to do some intensive research in, and I'll give it to Paul to tell you more about it.
Yeah, I think a couple of things to note here is, the failure to restore myelin, actually deprives neurons of critical support, right? So this is a major contributor to progressive neurodegeneration in multiple sclerosis. And, I think something else that's clear is that remyelination is almost unequivocally neuroprotective. So this is really a critical new therapeutic pillar in the treatment of multiple sclerosis, as well as other neurodevelopmental and neurodegenerative diseases. I think one other point that I'll note here is that the formation of new myelin in almost every case actually requires the generation of new oligodendrocytes from progenitor cells. And so what this means ultimately is that if we want to enhance remyelination in patients, that the path to do this is by stimulating the formation of new oligodendrocytes that are then able to go on to generate new myelin. I mean, this is pretty remarkable, right? Like it's we can't really stress this enough. The ability to regenerate an oligodendrocyte is pretty special, right? There's very few human cell types that have the innate capacity to regenerate after injury. So these cells are very special and clearly offer a therapeutically tractable target.
I think Paul brings up a critical point here too, which is really truly unique in the brain. Like this capacity to create or catalyze the brain's inborn capacity for repair. It really is just a remarkable opportunity for recovery, and it importantly sets the stage for us in thinking about repair more globally. But it's a critical step in the path for us for regeneration.
What role does age, or maybe we don't have the full answers to this right now, but what role does age or disease duration play in the potential for successful remyelination, and how should that inform clinical trial designs going forward? I know obviously in neurology right now, clinical trial designs, the ins and outs, the exclusion and inclusion criteria are very, very much a topic of controversy at times. So talk a little bit about the role that age and disease duration plays and how this might impact future trials going forward.
So I think it's a fantastic question. I think there's a very simple answer, which is we don't know. That's the simplest answer. There's a more nuanced answer, which is that it's almost certain that there are some subsets of patients for whom remyelination will be more potent and will be easier to measure without lots of competing factors. it touches a little bit on the point being made about the preclinical assessments, because the preclinical assessments, different ones are useful for different purposes. So some of them include inflammation in them and some of them don't. And that's super useful for us to disentangle the effects of inflammation from demyelination. I think loosely, people in the clinical space will sometimes think of demyelination and inflammation as superimposed, as if they're almost the same thing. But in reality, they're different biological effects. And that's important in thinking about measurement. It's important to think about the preclinical models. It's also important in thinking about when and how best people will get remyelinated and who's going to be most amenable to remyelination. One thing we know for certain is that people who lack an underlying axon, if there's no nerve fiber to remyelinate, remyelination is not possible. And there are lots of people who, even though that's seemingly obvious, there are people who undertake and investigate approaches for remyelination just in the wrong clinical context. We're all hopeful for therapies that'll have like a Lazarus effect and bring people out of wheelchairs and enable people who are severely disabled to restore some, if not complete, function. But we also don't want to create the unrealistic expectation that remyelinating therapies are going to miraculously have that effect, especially in the context where axons have been lost. And therefore, it's likely a mistake to investigate first remyelinating therapies in the context of people who have already suffered from severe disability. It may be important, almost in the same way that people in the cancer space, in compassionate use, utilize some of those therapies for compassionate use people with end-stage or advanced cancer. But it may not be the right way for efficiency for the field, and it may not be the right way to optimize the speed with which we develop these therapies for the broadest population of patients or people who are living with MS. So I think we've got to have that, sometimes difficult but nuanced conversation with people. I think when we have it in a way that reflects on all the nuances, people get it. But sometimes, and understandably, all of us who care about people who live with MS want to get the most effective therapies in the space as fast as possible. But we have to recognize that the way to do that might be in effectively showing remyelination in some narrower context so that we can expand it outward with success over time.
I think just to amplify the point, as with sort of most regenerative processes, remyelination effectiveness is generally thought to decline with age and prolonged disease duration. The definitive aspect of this in humans and whether or not it can be unlocked or reversed still remains to be seen, but generally thought that OPCs may become less responsive, or the CNS environment might be less permissive to remyelination with age, and certainly with disease duration where you have neurodegeneration, the opportunity to remyelinate and protect those axons goes away. And so I think what this means for the implications for clinical trials is really provides strong rationale for earlier therapeutic intervention strategies. Right, we know progressive neurodegeneration starts at the very earliest phases of disease and continues even in the absence of relapse activity, even on some of the very potent and effective immunomodulatory therapies. So I think the earlier we can replace lost oligodendrocytes in myelin, I think it's likely to lead to better outcome for patients. But the earlier treatments, come back to the question of biomarkers and imaging modalities, because you're now at a phase of the disease where there's sort of less going on. So the ability to accurately be able to say we've replaced or restored oligodendrocytes, back to quote unquote baseline or normal or improved above the disease state becomes even more challenging.
Well, I thought all that was quite interesting. And whether I like it or not, it does underscore the rationale for recruiting people with a shorter disease course, people who have not had MS for as long of a time. Because as Dr. Green points out, if we're going to make strides with remyelination, we have a much better chance if we use test subjects who have not had a lot of demyelination already, and certainly those who still have axons that can be protected. So even though, yes, I would really dearly love to be part of one of these clinical trials, I'm not the right subject for this, and I have to just recognize that. Still, I'm excited for that research that will help other people because there's still a lot of folks who could benefit from remyelination therapy. I know there's so much activity in the remyelination area right now. There's many teams of investigators working on the problem, but this seems to me to be a slightly different focus, and I'm thinking they might be onto something. So we'll keep an eye on this and see how it pans out. But in the meantime, what I always say, right? We need to keep taking really good care of yourself, and if you don't believe me, then you can hear from one of our investigators.
I think as a general statement, taking care of yourself and your body and exercising, getting sleep and doing things along those lines are generally good.
There you go. You've heard it from a guy with a PhD and probably much more besides. So in the meantime, I will keep you up to date on remyelination news whenever I hear it, and I'll see you again in my next video.